Okay, so after some initial issues, we are very happy to today have Lakshya Bhardwaj tell us about the discrete relationship between generalized and mirror symmetries. Take it away.
So if you recall, last year there was a very inauspicious news about the war in Ukraine on 24th February. And this year, on 24th February, I'm going to break another news, but this time is going to be a very auspicious one. So we know that there are mirror symmetries and there are generalized symmetries. And the news concerns the discrete relationship between these two symmetries. And you know, we should give credit where the credit is due. So full disclosure, our source is something known as solitonic defects, which was, so the source was described in this paper that appeared last year, and this news was broken in this paper in the January. Both of these papers are in collaboration with Mathew Bullimore and Andrea Ferrari from Durham and Sakura Schafer-Nameki from Oxford. So let me begin now. So we know that 3D n equals to 4 mirror symmetry is an infrared duality of two gauge theories. So here we have two 3D n equals to 4 gauge theories, 1 and 2. And we say that they are mirror duals if they flow to the same 3D n equals to 4 conformal theory in the infrared. More crucially, when they flow to this conformal theory, they flow up to an automorphism. So the Coulomb branch and the Higgs branch of these two theories are interchanged. And crucially, it's the infrared physics on the Coulomb branch that is exchanged with the physics on the Higgs branch, and vice versa. So this story first gained attention in these papers in 1996, and towards the end of 1996, we observed the seminal paper on this topic, which transformed our understanding about it, by Ami and Edward Witten, and it told us that mirror symmetry is a consequence of S-duality in type 2 string theory. So the question that I want to ask today in this talk is this mirror symmetry story true on its nose, or could there be some extra discrete modifications? So could it be that on one of the sites, I actually have to supplement the theory by some topological quantum field theory, as I show over here in red, which is in some way coupled to this gauge theory? Okay, so how would I probe such a question? Well, it's something topological, so it's going to impact topological properties of the theory on this side. And topological properties of quantum field theories, by definition, are captured by generalized symmetries and their anomalies. So what we can do is to compute generalized symmetries and anomalies of the two theories on both sides, the gauge theory 1 and the gauge theory 2, and see if they match or not. So if they match, everything is good. We couldn't detect any extra TQFT present in making mirror symmetry work. But if they don't match, then we have a problem. And then we need to find a TQFT along with the coupling of it to the rest of the gauge theory, such that the required mismatch between the symmetries and anomalies could be recovered. So we will pursue this, and what we will find is as follows. So we will see that generalized symmetries and anomalies are actually, the information about them is contained within information about various kinds of Hilbert series that you can compute. Or said another way, what I'm going to say is that topological information about our theories, 3D n equals to 4 gauge theories, is already contained in the supersymmetric information. So what we will see, so what we know already actually, is that if I take these two gauge theories, which are supposed to be mirror dual, then their Hilbert series match. So Higgs branch Coulomb series match the Coulomb branch Hilbert series on one side, And if you start with some baryonic Hilbert series on one side, you go to Hilbert series with background magnetic charges on the other side. But the key point is that they match, and this match has been explicitly shown in many examples, for example, in these papers. So if this statement is true, that symmetries and anomalies are contained within the Hilbert series, we are guaranteed that the symmetries and anomalies of the two theories are going to match. And going by the previous slide, it means that no extra TQFTs are needed to make mirror symmetry work. Now you can view it as another check, a discrete check for mirror symmetry, or you could see it as something boring. That's up to you. But during this process, what we learn is what is precisely the information inside Hilbert series that captures topological information. And so we learn what information is preserved along all kinds of RG flows. So we know that supersymmetric information is preserved along supersymmetric RG flows. But if I deform my theory by make it non-supersymmetric, then it's not necessarily preserved. But there is some subset inside Hilbert series which is preserved along even non-supersymmetric RG flows, which is the information about the symmetries and anomalies. Okay, so before I delve into the details, are there any questions about until this point?
Yeah, sorry, I have a question on the logic that maybe I'm not understanding, but if I try to apply the same logic, for example, to S duality in 4 dimension, so in that case, I know that it is required a coupling to a topological quantum field theory in order to precisely match S duality. I mean, SUN is dual to PSUN, but if I try to let's say understand this from computing anomalies, I will not succeed because SUN and PSUN have the same anomalies.
Right, but you will be able to detect it from right. So maybe there is some symmetry and anomaly inside it. So for example, in SO3 minus, you know that S duality has an anomaly with the one form symmetry, but it's not true in the other two frames, right? So if you include a large subset of symmetries and anomalies, you have a chance that you will be able to see the difference, right? But I'm not claiming that this is a definite proof that there are no extra TQFTs involved. This is just exploring this question by computing some symmetries and anomalies and seeing that they match on both sides. So we could not detect the extra TQFTs at this level. But of course, there might be some other things we are missing, some other kinds of symmetries and anomalies that might be able to detect the difference.
Okay, I see. Thank you.
Thank you. Are there other questions?
Sorry, I have a similar question. So I guess you will compute supersymmetric observables, no, in all the stuff. So it can be that the degrees of freedom which carry the anomaly are non-BPS. No, you cannot know.
Yeah.
Then you wouldn't detect the anomaly, but it will be there anyhow. I don't know any examples, but I don't know.
Right. So this can happen in 3D n equals to 2, but in 3D n equals to 4, all of the information about symmetries and anomalies is captured in there is a BPS representative of all of those observables. So this first time this was mentioned in these works of Kapustin and his collaborators around 2000. Yeah. Okay. But it's a general property of n equals to 4.
Okay, thanks.
Yeah. Okay. Other questions? Okay, so let me get into the details of the talk. Okay, so the first thing that we are going to look at are flavor algebras. This is a very well-known story. So what we know is that the Higgs branch flavor symmetry is supposed to be mapped to the Coulomb branch flavor symmetry. So there are two distinct flavor algebras acting as isometries on the Higgs and the Coulomb branches. And crucially, again, I'm highlighting it's the infrared Coulomb symmetry. So in these gauge theories, one of them, the Higgs branch flavor symmetry, is a symmetry rotating the hypers. So it can be computed by understanding what are the symmetries rotating the hypers. And on the other hand, the Coulomb branch flavor symmetry comes from by understanding what are the balanced gauge nodes. And there might, if there are some unbalanced ones, you have some extra abelian factors. Okay, so here is an example. So we know that these two theories are mirror duals. So here we have a U1, U2, and U1 gauge algebras, and here we have U2 gauge algebra, and this with edges are by fundamental matter. And the 2f and 4f just denotes that you have two fundamental hypers for this U2 and four fundamental hypers for this. So that's the notation I'm using. And now on the left hand side, there is an SU2 symmetry that's rotating these two fundamental hypers. That's the Higgs branch symmetry. And if I want to compute the Coulomb branch symmetry, that's SU4, because all these three gauge nodes are balanced and they form the Dynkin diagram of SU4. Okay. On the right hand side, I have four flavors. So I have an SU4 rotating these hypers. And there is a single balanced node, which forms the Dynkin diagram of SU2 Coulomb. And then indeed, at the level of flavor algebras, we see that the Higgs and the Coulomb algebras. So I'm mentioning only the infrared Coulomb algebras from this point onwards. So the Higgs and the infrared Coulomb algebras match, as shown over here. Okay, but now we want to involve some discrete information. So we can ask, what about the flavor groups? Do they match on the both sides? So first of all, we need to review what is the definition of a flavor group. So a flavor group for a flavor symmetry algebra F, the small f, is this capital F such that its Lie algebra is the flavor algebra first of all, and then it has to satisfy some additional properties. Okay, to describe these additional properties, we need to divide our local operators in the quantum field theory into two types, into genuine and non-genuine. So genuine local operators are operators which can just be inserted at any point in space-time, and they don't need to be attached to any higher dimensional operators. So this is a cartoon of a genuine operator. And on the other hand, a non-genuine operator is something that needs to be attached to something higher dimensional, some other higher dimensional operator. So it arises at the junctions of higher dimensional operators. So one of them is that it could arise at the end of a line operator. So here's an example of such a non-genuine operator. And now what we want this flavor group to satisfy is that all the genuine operators should form linear representations under this group. So just standard representations without any extra phase factors coming. This is not true for non-genuine operators. So we allow the group to act projectively on non-genuine operators. And moreover, what we want is that somehow this should be a group which is the smallest group that acts linearly on genuine operators. So they should have a faithful action on genuine operators. So let's try to understand what I'm saying in this simple example. So suppose the algebra was SU2 and the group was SO3, which is the simply connected group SU2 modulo the center is E2. Then in this case, if this is the situation, then all the genuine operators form representations of this algebra, but only those representations which carry integer spins. These are precisely the representations of the group SO3 as well, so it acts linearly. But on the other hand, non-genuine operators may form representation half integer spin representations. And these are representations of SU2 group, not SO3, and SO3 acts projectively on them. So for example, if I start with the identity element in SO3 and go around in a circle and come back to identity, the operator transforms by a minus n. Okay. So now we want to understand what are the flavor groups corresponding to the Higgs branch and the Coulomb branch flavor symmetries we discussed. Okay, so we want to discuss genuine local operators in the gauge theory. So for the Higgs branch operators, which are genuine, are simply gauge invariant combinations of hypermultiplets in the gauge theory. So that's the concrete computation that we can perform to compute them. On the other hand, the Coulomb branch operators are monopole operators, and these are the standard monopole operators. You pick a U1 inside your gauge group, and you turn on a sphere around it, you turn on a field strength for that U1. Okay. So how are we going to compute the Higgs and the Coulomb branch flavor groups, which I am denoting as FH and FC over here? So for the Higgs branch, the computation is straightforward. You computed the gauge invariant combinations of hypers. You check what kind of charges they form under this algebra FH. And then from that, you can try to read if there is what should be the smallest group that under which all of these charges form linear representations. Okay, for the Coulomb branch, there is one more complexity involved because we have to look at the infrared Coulomb branch. So as we know, we know that how these monopole operators transform under various U1 Coulomb symmetries arising from the unitary gauge nodes in the ultraviolet. And Gayotto and Witten provide us with a map of how these U1s are going to reorganize into U1s living in the maximal torus, in the Cartan of the Coulomb flavor algebra in the infrared. So we can also compute what are the weights that these monopole operators are going to form. And from this information, we can compute the group. Okay. But there is an extra step involved on the Coulomb side. So all of this is well known and has been explored in the last decade in the literature as well. Right. But what I want to point out today is that the final expression for the Coulomb flavor group takes a very nice form in terms of the quiver. Just like the infrared Coulomb branch flavor algebra could be read from the balanced nodes. The Coulomb flavor group can also be read from the balanced and the unbalanced nodes, but you need to just observe where these unbalanced nodes are going to hit the balanced nodes. So here I'm drawing a cartoon of some 3D n equals to 4 gauge theories with unitary gauge groups, which has some balanced and unbalanced nodes. So there are some balanced nodes which are shown as white dots, and there is an unbalanced node here, which is shown as a black dot. And this black dot is hitting the white dot at some particular point in this. Yeah.
Quick question: when you say unbalanced, it's always overbalanced, right? Positive balance.
Yes.
Okay. Okay. Good.
So I always want to flow to a conformal theory. Yeah. Okay. Right. So this unbalanced node is hitting the quiver formed by the balanced nodes at a particular location in the Dinkin diagram, the Coulomb branch flavor algebra Dinkin diagram, and this node is associated to a particular highest weight representation. So for which the Dinkin coefficients are all 0 except 1 at this node. Okay. So let's call this representation R. Then what you need to include in your calculation are monopoles transforming in this representation R for this balanced Coulomb flavor algebra, and also having charge 1, which I'm denoting here as a subscript 1, under this U1 coming from the unbalanced. And similarly, and so you have to do it for all the unbalanced nodes and include them in your calculation, and you can compute the Coulomb flavor group. You do not have to compute a lot of terms in the Hilbert series. This diagrammatic way gives you the correct answer. So it gives you an easy way to read off.
But what do you do in the cases where it doesn't work?
Which cases, sorry?
There's plenty. Take the simplest. It's plenty. I mean, we could discuss a specific example. What do you do when it doesn't work?
So there might be sometimes
So the
multiplicities involved.
simplest example would be the modular phase of instantons described as a Coulomb branch. If you have multiple instantons, but maybe we can do some examples later. But yeah, in general, so this is a good rule, but there are counterexamples for this to work.
Yeah, I am assuming that I am in this in the good quivers. Right?
No, good quivers.
Very good. They are very good.
For good,
excellent. They are excellent.
Okay.
Not just good.
yeah,
Okay,
but even for good quivers, this rule to read off the representations that the monopoles will transform under is this doesn't give you enough sometimes, doesn't give you all the generators. And also you can have extra U1s which appear in the IR that you don't see in the UV. So this can complicate things further. And they can enhance to non-abelian,
right.
a bigger non-abelian.
I'm not including the emergent symmetries. Yeah. But
Yeah.
I have a derivation for this rule, so we should discuss this. Yeah.
Okay, so you just, at the moment, you just consider cases where there is a correlation between this combinatorial condition and the global symmetry and the algebra of the global symmetry?
Yes. And I believe these are good quivers involving unitary gauge groups. This should work. But we should discuss.
Unitary.
Not for all, but okay. Let's discuss this later.
Okay. Yeah, so as you can see, all of this is well known. This has been explored a lot in the literature because we are only computing some Hilbert series so far, just normal Higgs and Coulomb branch Hilbert series. Okay, so let's see again how this works in these examples. So this is the same example that we had on a few slides ago. And now we want to read what are the Higgs and the Coulomb flavor groups. So let's begin on the left-hand side. Here we had an SU2 algebra rotating the two flavors, but the group associated to them is SO3, and that's because the Z2 can be cancelled by the gauge transformations. So it doesn't act on the genuine operators because gauge transformations do not. Okay. And similarly, on the right-hand side, we will have to take SU4 modulo the center Z4. So we have to take the PSU4 as the group. And here for the Coulomb symmetry, if we apply our rule, everything is balanced. There are no unbalanced ones. So we have to, we only generate adjoints of SU4 and no other representations. So the Coulomb group is PSU4. On the right-hand side, again, the same logic works. You only have adjoints. So you have SO3 Coulomb, and then they match. So let's do another example where there are some unbalanced nodes to see how it works there. So here, this is another example of mirror duality. Right, so on the left-hand side, we have a Higgs. Let's first compute the Higgs group. We have an SU2 coming from here and a U1 coming from the single fundamental. But there is the Z2 of this SU2 can be cancelled by the Z2 inside this U1. So you have a U2 group of Higgs branch symmetries. On the right-hand side, you have the same logic as above. You have a PSU4. For the Coulomb group, here the first two nodes are, so all of these three are balanced. There are no unbalanced on the left-hand side. So we have PSU4. On the right-hand side, the U1 is balanced, but U2 is unbalanced. So we are going to obtain operators transforming in the fundamental of this because the unbalanced hits the balanced node, which corresponds to fundamental representation. And it carries an extra charge under the U1 coming associated to the U2 gauge. So this means that it lifts to actually a fundamental of a U2. So the Coulomb group is U2, and these groups precisely nicely match. Okay, so this was a discussion about the groups, but now one could ask, what about the anomalies of these flavor symmetries? Can I compute the anomalies, Hooft anomalies, and match them? So this is encoded in the non-genuine operators. So recall to understand the flavor groups, we discussed the genuine operators, but to discuss flavor Hooft anomalies, the discussion centers around non-genuine operators. And the kind of non-genuine operators we are looking for can be understood as monopole operators for the flavor group that you have computed, for the flavor group F. So in general, such monopole operators are actually non-genuine because they have to be attached to a vortex line for the flavor group. So what this means is as follows. Both of these operators, vortex line and monopole, are defined by picking a map from U1 into the flavor group. And then, so let's call this map phi. Now you have got a U1 inside your flavor group, and you can turn on a field strength for this phi on a disk as you intersect this line operator, vortex line operator, and you impose this to be 1. This defines for you a vortex line defect. And if you do it on a sphere surrounding the monopole and impose it to be 1, that defines for you the monopole operator. Okay. Now the statement of anomaly is as follows. So if these monopole operators, these flavor monopole operators, transform not linearly under the flavor group, but transform projectively under it, then there is a non-trivial Hooft anomaly for the flavor symmetry. And this is actually a much general phenomenon. So both of these two defects, they are inducing some background fields for the symmetries that you have. So and they're solitons for this reason. So we can call them solitonic defects. And in general, whenever solitonic defects are themselves charged under the symmetries, then that's an indication of Hooft anomaly, which we discussed in our paper last year. And this is precisely the case where the solitons are the flavor monopoles. Okay. So are there any questions at the moment? I'm going to now discuss computations of such anomalies. Okay. Right. So earlier we saw that flavor group could be read from the location of unbalanced nodes hitting the balanced nodes. Okay. In a similar way, these anomalies can be read from the locations of flavor nodes hitting the balanced nodes. Okay. So we have a situation of this kind. Here now a black square means that I have a flavor node and it's hitting a set of balanced nodes. And the place it is hitting corresponds to some representation R. Okay. So what this will construct for us would be some monopole operators for the Higgs branch flavor group. And we will see that these can transform projectively under the Coulomb branch flavor group. So there's going to be a mixed anomaly between the Higgs and the Coulomb branch flavor symmetry. And these monopoles can actually be captured using Hilbert series. If you study Hilbert series with background monopole charges, you can study them. You can capture them in these Hilbert series. Okay. So whenever we have this kind of situation, it turns out that you have flavor monopoles in your calculations for the anomalies. You need to include flavor monopoles transforming in a representation R of the Coulomb flavor symmetry algebra. But these are flavor monopoles for the Higgs branch flavor symmetry, in particular for this square black box flavor symmetry. Okay, so let me again go back to this our example that we have been discussing through this talk. So we saw that there were SO3 and PSC4 symmetries, and they were nicely matching each other on both sides. Now we want to compute Hooft anomalies for these symmetries and see whether they match or not. Okay, so on the left hand side, we have flavor nodes are hitting the antisymmetric representation of the SU4 Coulomb algebra. So if you are looking at monopole operators for SO3, they are going to transform under SU4 Coulomb as antisymmetric. On the right hand side, I have now monopoles for PSC4, and they're hitting the fundamental node. So they are going to transform in the fundamental of the SU2 Coulomb. Now, I claim that both the anomalies associated to both of these are exactly the same. And the anomaly takes the following expression. It can be given an expression in terms of an anomaly theory, which is written in terms of some characteristic classes associated to the PSC4 and SO3. So they match up to the interchange of Coulomb and Higgs, of course. So an easy way to see that they will match is as follows. So you know that lambda 2 is order 2, because if I take tensor product of lambda 2 with itself, I generate representations of which have zero charge under the center of SC4. Similarly, fundamental is of order 2. If I square it, I only generate representations which have zero charge under the center of SU2. So both of them are order 2 anomalies, and the only order 2 expression that you can write down using a Z4 and a Z2 valued classes is this one. More precisely, this W2. So let me focus on one of the sides. On the left hand side, W2H is just the Stiefel-Whitney class, which describes obstructions of lifting SO3 Higgs bundles, SO3H bundles to SO2H bundles. And W2C is a Z4 valued class, an analogous one which describes obstructions for lifting PSU4 bundles to SU4 bundles. Okay. Right. So are there any questions at the moment?
You have 6 different values for the SU4 Whitney class?
4 values.
So why did you call it lambda 2? SU4?
Lambda 2 is the antisymmetric.
So this is 6-dimensional.
Yes, 6-dimensional representation.
So you have 6 different values?
No, it's not associated to that. This Stiefel-Whitney class W.
This is a map. This arrow denotes a map?
Yes, it denotes a map. That if you have monopole operators transforming in the 6-dimensional representation of SU4, and they were SO3 monopoles, then you can associate to it this anomaly theory, which is a 4-dimensional theory.
And so the phases, the different phases, you have 8 different phases that they could be?
No, there are 4 possible things because you have a Z4 valued class W2C, and it's Z4 valued because the center is Z4.
Yeah.
So this lambda 2 is sort of 2 inside Z4. So it gives you a factor of 2 here.
Yeah, the Z2 subgroup of,
yes.
And then the H, you have Z2, right? So 2 values.
Yes.
So
that has only 2 values.
2 times 2 different values, you say?
Yes.
Okay, thank you.
Yeah. Okay, so are there any other questions?
Actually, yes, I have a question. I don't understand. So when you say that this transforms projectively, and then you understand this as the anomaly, why is it mixed between the 2 sides, and can it not be like an anomaly for the one and an anomaly for the other?
Right. So if we go back over here I was just looking at the full flavor group F, and we were looking at monopoles for F, which could transform projectively under F. So there was no difference between 2 kinds of symmetries. There was just a pure symmetry. But what happens in n equals to 4 theories is that F decomposes as a product of the Coulomb and the Higgs groups. And then the Higgs monopoles are transformed into the Coulomb group, and the Coulomb monopoles transform into the Higgs group. And that's why this anomaly, which is pure on the full product group, becomes a mixed anomaly between the 2 factors.
Okay, thank you very much.
Yeah. Okay, so this finishes the main part of my talk, where I said I would be exploring whether there are discrete modifications needed to mirror symmetry. We have seen that flavor symmetry algebras, flavor groups, and even Hooft anomalies for flavor symmetries nicely match in this class of examples where we have unitary 3D n equals to 4 theories. Okay, now I'm going to shift gears a little bit and describe how all of this technology can be applied to magnetic quivers of higher dimensional theories, and how we can determine flavor symmetry groups of higher dimensional theories by studying the Coulomb flavor groups of magnetic quivers. Okay, so first of all, I want to slightly go beyond unitary gauge nodes. I want to start introducing special unitary gauge nodes. Okay, and the way I'm going to envision doing it is that I take this the flavor box that I have, and I just gauge it by an SU gauge group over here. So I obtain some SUN gauge group. Okay, what happens during this process is that I generate a one-form symmetry typically. So in general, if the quiver is complicated, you can get some complicated one-form symmetry. I'm simplifying my life and assuming that this whole ZN center can be cancelled by the centers of the other unitary groups. So I generated ZN one-form symmetry in this process. Okay, and I want to focus on what happened to this configuration of operators that was giving rise to the Hooft anomaly. So before gauging, we had a flavor vortex attached to a flavor monopole, which was possibly charged projectively under the flavor group. So a Higgs monopole was charged under the Coulomb group. Now, after gauging, what happens is that this flavor vortex becomes is now sourcing a background for the one-form symmetry. So earlier it was sourcing a background for the Stiefel-Whitney class W2 for the Higgs symmetry. This becomes the background for the one-form symmetry, B2 for the one-form symmetry. And so it becomes a solitonic defect sourcing one-form symmetry. And these are precisely what one-form symmetry generators do. In 3 dimensions, they're topological line operators. So the fact that it's topological now, I'm highlighting it by making it blue. And now this flavor monopole, because I've gauged the Higgs flavor symmetry, now becomes a gauge monopole. But it's not a usual kind of gauge monopole, because the usual gauge monopoles are genuine local operators. Rather, this is non-genuine. It lives at the end of a topological line operator. We can call such monopole operators as fractional gauge monopoles. And the reason is very simple, that if you take n copies of this thing and fuse it, the line disappears because it's Zn valued, and you are left with a normal gauge monopole. So it's 1 over n of a normal non-fractional gauge monopole. And this anomaly, mixed anomaly that we had between the Coulomb and the Higgs symmetries on the before gauging, the Higgs symmetry now gives rise to one-form symmetry, so it becomes a mixed one-form anomaly with the Coulomb zero-form symmetry. Okay, so this is just some theoretical manipulation so far. But now let's take one extra step. Let's now gauge this one-form symmetry. So this is usually known in the literature as removing the Zn center, that I want to mod out the Zn center. And the gauge group is then product of all of these unitary groups times the special unitary modulo diagonal Zn. Okay. So I've gauged this one-form symmetry. What happens to this configuration? This one-form symmetry generator, it was generating one-form symmetry, but since I gauged the one-form symmetry, it becomes invisible. It becomes the identity line operator. And the fractional gauge monopole now just becomes a genuine non-fractional monopole operator. And notice that this label R throughout has not changed. So it transformed from a flavor monopole operator to a fractional gauge monopole to a non-fractional gauge monopole, but it's still in this representation R. So just from the simple arguments, we have deduced the existence of non-fractional gauge monopole operators in this theory, which carry this representation in such a theory. where I have a special unitary and I remove the associated one from symmetry. Okay, so now this is going to modify the Coulomb branch flavor group. So what is the modification? Right, so the modification is simply that wherever the special unitary node is hitting the balanced nodes, that's the monopole operator that you have to include. Earlier, we saw something similar. We had a unitary node, unitary gauge group hitting the balanced nodes. And then we had to include a representation for the balanced ones, but also it had charge 1 under the U1 coming from the unitary node. So we don't have that U1 anymore, and we don't have to include that charge. Okay. So this is also sometimes, it can also, the previous theory is also referred as follows, that instead of special unitary node, I had a unitary node instead, and I removed the diagonal U1 from it. So there is an extra prescription to remove a U1 from the gauge group. So this setup is going to have a genuine monopole operator in this representation R of the Coulomb symmetry algebra. Okay, so we have learned this fact, and now we can use this to quickly compute various flavor groups. So here is an example. So let's study 5D SCFTs. I want to take an example. This is the 5D SCFT, which admits a mass deformation to 5D supersymmetric gauge theory, having SP2 or USP4 gauge algebra with 9 fundamental hypers. Okay. The magnetic quiver for this has been computed in the literature, and it takes the following form. You have an SO20 balanced configuration. You have an unbalanced node hitting one of these nodes, and you are instructed to remove a diagonal U. Okay, so it's known that you can remove the diagonal U1 at any location, but since we observed something interesting when we remove U1 from the unbalanced node, let's remove that U1, and then we have to just include a monopole operator corresponding to the representation in the representation corresponding to the node to this Dinkin node in the Dinkin diagram for SO20. And this is either the spinner or the co-spinner. Let me call it spinner. So I can quickly see that the monopole operators, the genuine monopole operators in this magnetic quiver, form a spinner of the SO20 flavor algebra. And so I'm looking for a group which admits spinner representations, but does not admit co-spinner and vector representations of SO20. And this group is known as SS20, where S is for spinner. And this can also be, so we have now managed to derive the flavor group of the 5D theory, not just the flavor algebra from its magnetic quiver. And this can be confirmed using the Coulomb branch analysis, from a Coulomb branch analysis as well. So what I'm saying is that this was a Higgs branch analysis because we used a magnetic quiver. And there is a independent Coulomb branch analysis that reveals the same flavor group for this 5D conformal theory. Okay, and you can generalize to 5D SCFTs. And there is a very nice uniform generalization also to 4D n equals to 2 classes theories, where you also have these star-shaped quivers and you're instructed to remove a diagonal human. And there you could remove it at the central node of the star-shaped quiver, and then match the flavor group that you compute that way, which uniformly across all examples of type A classes matches precisely the prescription that is given in the literature using the compactifications of where you just directly use the compactification of the 2,0 theory and how the surface operator is compactified in this process. Okay, so this passes the rule that I described today passes all of these interesting checks, and now it can be used to do some new computations. And this brings me to the end of my talk. So we discussed a lot of things. So let's summarize them. First of all, we found no evidence for the need of a discrete modification of 3D n equals to 4 mirror symmetry. And this is in the class of theories which involve unitary and special unitary gauge nodes. Okay, we did this by computing some generalized symmetries and their anomalies, and we found that they match beautifully across the proposed mirror duals, and we don't need to modify them. But this doesn't mean that there cannot be any modification. There might be some symmetries and anomalies we are not considering, for example, for some higher groups or some non-invertible symmetries or something else out there, which might not match between the two. And also, this is only restricted to this special class of theories. So as you go beyond this class of theories, maybe to orthosymplectic quivers, things might get modified, where there is some potential because there's lots of Z2s floating around. So there might be some subtleties involved there. We should check it in future work. The second point is that, so these generalized symmetries and anomalies were computed using the monopole operator. So they could have been observed in the Hilbert series using the standard monopole formula, but various different kinds of Hilbert series that counts non-genuine operators as well. And the general imprint of that was in general theories with or without supersymmetry in general dimensions, generalized symmetries and anomalies can be encoded in solitonic defects. In the special case of 3D n equals to 4, the solitonic defects are vortices and monopoles, so it can be captured in all of these nice things that we have studied. Okay, so I should mention at this point that you can apply the same logic also to non-supersymmetric three-dimensional gauge theories and compute the symmetries and anomalies by studying their monopole operators. And we did it in our paper last year as well. Okay, then the third point is that in this class of 3D n equals to 4 theories involving unitary and special unitary gauge nodes that we are looking at, generalized symmetries and anomalies can be simply read from the positioning of unbalanced or the flavor nodes with respect to the positioning of the balanced nodes. So that comes in very handy. That gives you a quick visual way of computing these things. And the last point is that all of this technology that was developed in this context, that I presented in this context of mirror symmetry, can actually be applied to magnetic quivers. And this can then be used to compute flavor groups for higher dimensional superconformal field theories, and possibly also other kinds of higher form symmetries and anomalies that we haven't looked at, but it would be a nice, interesting future direction. So let me end with some outlook. So there have been a lot of works recently on discrete aspects of 3D n equals to 4 theories. This is a short list of the papers that I could compile. And there seems to be there's a lot of scope for exciting opportunities in the future with all the exciting development in the field of generalized symmetries, especially with the advent of non-invertible symmetries and so on. So we should continue to explore it, and we will find many exciting physical applications in this context. Thank you very much for your attention.
All right, let's thank Lakshya. Questions?
So I can ask maybe one naive question. In some of these theories, when you have hypers with charge which is not one, then you have non-trivial two-group symmetries. But here in those quivers that you looked at, where all the hypers are charged one and all the ones, is there a non-trivial two-group symmetries?
Yeah, no, not in these cases.
So it's really guaranteed that whenever you have just this quiver, like simply laced, unitary, etc., there can never be a non-trivial two-group symmetry, right?
Yeah, at least the Higgs branch one, because we're only studying the Higgs branch. Yeah, but if you go to orthosymplectic ones, then there can be in straightforward curves. Sure. Like in spin for M+2. Yeah.
Okay.
But unitary, I think, is a general result. Even in the classifications we performed in 6 dimensions and 5 dimensions, there was this pattern that if there's a special unitary node which behaves like the unitary node, then there cannot be any two.
Okay, thank you.
Yeah.
More questions? Okay, maybe I can ask one about the computation of the anomalies. So is it so what I understand is basically you just check whether the representation is realized projectively. Is this the idea
Yes.
generally?
Yeah.
Okay, good. So this is how you always compute, or are there other techniques that you use to compute anomalies in this setting? I mean,
no, that's it. So first you need
that's it.
to.
Okay, so that's actually quite it should be quite simple in general. That's quite nice. Okay.
So you pick a monopole first, and monopole. Then you look at whether it can be lifted to a monopole for the simply connected group. And there is an obstruction given by an element in the center. So there is an element of center associated to the monopole. And then you compute its charge under the center. So then you obtain a map from the center to its dual, and that computes the anomaly for you. So I didn't describe it, but then the final expression takes this form in this example.
Very nice. Okay, do we have more questions for Lakshya? All right, then I'd say let's thank him again.
Thank you for having me.
And I will stop the recording.